Good evening from Bangladesh. I'm Hussain. We have been organizing lecture series on extracrystallography and solid-state chemistry. It is our 23rd lecture on structure of solids. Well, the last lecture, that is 22nd lecture, we finished with this slide. We were talking about density of closed-packed structures. That's what we were talking about. And we showed a figure like this in our earlier lecture, that how we packed closed-packed structures being done. The one thing we do have to remember that we are quoting that this sphere of only one size. That is what we are assuming, and then we are keeping it in contact with each, and then we perpendicular to this plane of paper, we are staking one net after one net after one net, like this. And then what would be the possible maximum density of this sort of closed-packed structure? That's what we can calculate. And as I said, that we have to first say that the spheres are only one size, not in different size, same size. Okay, then we know also in a cubic closed-packed arrays, the face-centered cubic unit cell, and we also discussed that a face-centered unit cell has got only 4 spheres. And if we know that it is only 4 spheres, and if we have the size of the spheres, and if we call that the size is R, then we have 4R will be the total sphere. And then what we can say, we take this unit cell, and from A is equal to this is the 4R, that is the sphere, this is sphere, that's the 4R, that is 2R, and the total diameter, and this is radius of one sphere and radius of another sphere. So this is 4R. And with this, we can, using Pythagoras theorem, we can calculate the total volume in the unit cell, and that we can see that it is 74. That means we can say that 74.05% space is being filled by this closed-packed structure. Similarly, we can find out the hexagonal closed-packing structure and find out that it is also 74.05%. Okay, then we have 74.05% with these spheres to filled in a closed-packed structure. What are the rest then? How we fill this rest things? And we say that this hexagonal closed-packed and cubic closed-packed has got 74.05%. But if we have a non-closed-packed structure, the density is lower than that of closed-packed structure. We take an example, and that is body-centered cubic structure. There we see that density is being 68.02%. Okay. Now we go for next, how we assign atomic coordinates then. That what is also a very important factor for describing structures. Okay, so then we see, whatever books you find out, that you will see that a cell, a unit cell is drawn as an oblique projection, like this. Unit cell is drawn. But then this description is not is become ambiguous. We need an unambiguous description, and we said it before that we have to project the unit cell down a particular crystallographic directions. That means either A direction or B direction or C direction. So if we do that, then it comes up like this. Then what we are doing, we are taking z-axis onto the AB plane. That means z-axis is perpendicular to the plane of paper, and this is AB plane. And then we have to find out the coordinate of this. And this is what is origin then. We have in the corner two atoms. One is up and one is at z is equal to 0, another is z is equal to 1. Similarly, that corner, this corner, we have this coordinate for a C value 0 and 1. Then we come to the next four atom, say sphere. Here is the 1, and that we see that the z value is half. Here is another one, the z value is half. Here is another one, the z value is half. And here is another one, z value is half. If we now just take the AB plane, not thinking about thinking at z value 0, 0, half and half. How can we get this functional coordinate? It is a origin of the lattice point, and in the origin, if at the left corner, we'd call it origin, and here it is 0, 0, 0 value. That means A is equal to 0, B is equal to 0, and Z is equal to also 0. If we come here, then what happened? That this is a Z is equal to half value, and then it is the half of the A unit cell. So the position is here is half 0, B is 0, and Z is equal to half. That means we are talking about this coordinate now. And then if we come to here, what is it? B is equal to half, Z is equal to half, and A is equal to 0. So this is the coordinate we are talking about. And similarly, we can find out the four coordinate of the this projection. That's what we are talking about, how the atomic coordinates being represented in a AB plane, or let's say that XY plane or YZ plane or ZX plane, depending on which axis we are taking perpendicular to the plane of paper. Okay, we go to next slides. We know, by now we know that fractional coordinates in the unit cell is customary 0 and less than 1. Less than 1. The coordinate or with coordinates is greater than 1. Okay, so we are taking here 4 unit cell here in this figure, 4 unit cell, and we want to find out the coordinate of this atom. Let's say this atom, or 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 this atom. So the x direction is here. It is the positive direction of x1, and the negative direction is here. And z direction over here is a positive direction. Over here is the negative direction of z. And then this is the y direction, and this is what is positive direction, and this is what is the negative direction. Okay, so if it is so, and this is an atom, let's take this atom then. That will be easier to say. You see, x is equal to half, y is equal to half, z is equal to 0. And then corresponding to this, another unit cell, it will be half z is equal to 1. If we go down, it will be half z is equal to -1. Similarly, if we go this way, x will be -half, y half, and z is equal to 0. If we go up there, x is equal to -half, y half, and z is equal to 1. And go down, we can have -half, half, and then -1. This is how we assign fractional coordinates of atoms. But here I have to say that this assignment is so clearly done if we go to space group in International Table of X-ray Crystallography. Every space group there, we have having equivalent position and atomic position is how to assign those is clearly mentioned there. Okay, now we come to this. So far we have discussed closed spec structure, and now we will say which are the elements could possibly can give us closed spec structure using this close packing system. So the metals, we will see that most metals crystallizes in three of this arrangement, either cubic close packed structure or hexagonal close packed structure or body-centered cubic structure. Body-centered cubic structure, close packed structure. The first two are close packed, but the body-centered one is not close packed. We mentioned it in the earlier slides. Okay, in this table, we see some of the metal and their structure, how we describe the structure. For example, copper. We say the copper is cubic close packed structure, and then the radius of this copper, we say that is 1.28 angstrom, and the unit cell is 3.6147. Now, please do remember the cubic close packed structure. That means cubic unit cell is A is equal to B, B is equal to C, and then alpha is equal to beta, beta is equal to gamma, and which is equal to 90 degrees. So we have only one parameter, which is independent parameter, that is A. So what we get is some of the metals here, and they are cubic close packed, and you will see that the radius is different, and the cell parameter is also different. So cell parameter is also different. So therefore, we will say that there's nothing that we can say which metal will have this hexagonal close packed structure or cubic close packed structure. That we cannot take this radius, or we cannot see the cell parameter. By this, we cannot say exactly which one is having hexagonal close packed structure, why and how, and which one is having close packed. So there is no norm about it, but probably the fine details will be the bonding requirements and bend structure of the metals, this fine detail. So I would say there is no one reason, specific reason, saying that this metal will be crystallizing with cubic close packed structure, or that metal will be crystallizing with hexagonal close packed structure because of this reason. That we cannot say now, still now we cannot say this. Okay, but structure is like this. Alloys. We know that there are alloys, intrametallic phases. We call also it's a solid solution. So for example, we take copper. Copper is cubic close packed structure, and gold. Gold is also cubic close packed structure, and one is 1.28 angstrom, and another 1.44 angstrom. And then this we can have alloys between copper and gold at high temperature, a complete range of solid solution between copper and gold forms. And in this case, distribution of copper and gold are statistically over the lattice point in the face-centered unit cell. So cubic close packed layers, is it a random mixture of copper or gold? We could say random mixture of copper and gold. What about then if we take high temperature? I said it is high temperature, but what about if we anneal it? Anneal, that means we cool down this, and then what happens, the arrangement of the order of copper and gold, and we can have two intermetallic phases, or gold and copper, and gold copper 3. So, and then this, we will see that this is no longer a statistical arrangement. It is order disorder phenomena is occur commonly in both metallic and ionic structures. So here are some examples of cubic close packed structure, hexagonal close packed structure, and body-centered cubic structure. So of some metals, what we call. And then we go for the next slide. And next slide, what we are talking about, we talked about the close packed structure and said that it has got 74.5%. Is it? Yeah, let's say it has 74.05%. And then we will, what about the rest volume? what happens then? Then we call it there are voids or interstitial sites or words. Then we will see that there could be two different types of sites, void sites. There is tetrahedral and one is octahedral. Are present in cubic closed spec structure is that what we showed, how a tetrahedral voids is occurring. We have base, 3 spheres, and then on top of that we have this, and then we see here is a void created. Here is void. If we take that one, then this atom is below the base plane, and then we see that there is another type of void creating, and this is also tetrahedral. So we call there are T plus and T minus depending on the projection, that we will get 2 types of tetrahedral voids in closed spec structure. And that's what we have shown here, that if this is a A layer and this is a B layer, we have tetrahedral T minus and we have tetrahedral T plus. So tetrahedral voids could be 2 types, T plus and T minus, depending on the arrangement what we have in the earth. Okay, then we go for octahedral arrangement. What is octahedral arrangement? You see that we have 3 layers of sphere up and 3 layers of sphere down. And then we create a void over here, and that is what is octahedral void. So if we take this A, and if we say this is B, then we get octahedral voids here. And more specifically, we can show this how octahedral voids are. There will be the octahedral voids. This is a sphere 4, and this is another 2, 3, 5, 1, 6, and this is octahedral voids. But more specifically, you can show with the layer of closed spec the position of tetrahedral voids. This is a tetrahedral void, tetrahedral void, tetrahedral void, tetrahedral void. And if we say this is T minus, tetrahedral void, and then this tetrahedral void is T plus, you see. And this we have octahedral voids and octahedral voids. So various type of voids, both octahedral and octahedral, tetrahedral, 2 types, T plus and T minus, and octahedral has been shown here. Okay, now we go for a little bit more specifically. We want to see the octahedral voids and tetrahedral voids when we draw a structure like this. Where is octahedral voids and where is tetrahedral voids, etc. It is, if we look for the voids, it's very easy to see the octahedral void, mid-center of the this is the celeste, this is anion, this is an anion, this is a cation, where is the octahedral voids are there. Similarly, this is one is octahedral voids, this one is octahedral voids, so this one is octahedral voids. So its octahedral sites are easy to locate. But if we talk about tetrahedral site, we have to take this figure first. So this is every anion, every corner, every alternate corner, we have anion here, anion here, anion here. And that makes a tetrahedral void. And if we say this one is T minus, the other one will be T plus. Okay, and we can find out also the mx distance by taking this one. And this is also a figure where we can see the symmetry elements. What are the symmetry elements we can have with these spheres? But a 2-fold rotation axis and a 4-fold inversion axis here, and then a 3-fold rotation axis here. So symmetry rotation plus tetrahedral sides positions and octahedral sides position are being shown here. Okay, now we go to the next slide and talk about the various coordinates. What is the coordinates? If we take the octahedral sides, very easy to get the coordinate. And if we have considering the origin, we are talking this is 1, this is 1. So it will be, let's say this is A, so this is half, and then 0, 0. If we go to B, let's say this is Y, and that means V, and it will be 2 will be 0, half 0. 0, half 0, and if we go to 3, this is Z, so 3 will be 0, 0, half, and if we go for 4, we will say that half, half, half. This is how we get the octahedral coordinates. And similarly, if T plus, we have this coordinate. This is the coordinate we are talking about. And then tetrahedral minus, we will see this is the coordinate we get. So there are 1 to 5, 1 to 12. We see where are the tetrahedral plus and tetrahedral minus and octahedral coordinate systems. Okay, now we talk about a little bit of, and we take this slide in next lecture also, little bit of ionic structure. For example, let's ionic compound, sodium chloride, aluminum oxide, sodium oxide, zinc oxide, how we can describe the structure of these elements, let's say, and in terms of close spectrum arrangement. So we said that we have two types of close spectrum arrangement. Close spectrum, here is cubic close spectrum arrangement. And if we take the anion as a close packing, because anion size is larger than the cation, and if we put the cation in the interstitial sites, then if there is no cation in the interstitial T plus or T minus, only full octahedral, all octahedral sites are filled up, then it becomes sodium chloride structure or rock salt structure, rock salt and sodium chloride structure. This is how we describe. Similarly, we come to here, and then if we have sulfide as a ion, as an anion, and it is having a cubic close spectrum arrangement, anion arrangement, and then only T plus interstitial sites are filled up, then we describe this as zinc sulfide or zinc blende or sphalerite structure. Similarly, if we fill up 1/8 of tetrahedral plus and 1/8 of tetrahedral minus and 1/2 of the octahedral sites, and rest are anion is the closed spectrum site. And if this is this arrangement, then we call it spinel structure. That means oxygen will be in the cubic close spectrum arrangement, anion arrangement, and then magnesium and aluminum will fill up these sites accordingly. This is how we describe. We take an example of cadmium chloride. Chloride ion having a cubic close spectrum structure, and half of the octahedral side will be filled by cadmium. 1/3 will be of the octahedral side will be filled by chromium, and that is what we call cadmium chloride structure, chromium chloride structure. Well, so far we have discussed this. Similarly, we can describe about hexagonal close spectrum structure and get that nickel arsenide structure, zinc blende, which is urzite. This one is sphalerite, and this is another polymorph, which is urzite structure. We can describe like this: cadmium iodide structure, rutile structure, aluminum alpha aluminum oxide, that is corundum structure, and olivine structure. So you can see that we can use this closed spectrum arrangement and fill up the interstitial sites, and then we get many structure which are mineral structure, and also some synthetic structure also you can describe it. And I will come to the next lecture. We'll talk this a little bit more, and then go for finish our closed spectrum arrangement of describing crystal structure, and then we start polyhedrous space filling polyhedra type of describing structure. Thank you very much for this lecture, and we talk in the next lecture the rest of the structure of solids. Thank you very much.